Welcome back, everybody. Today we're going to explore the notion of an inner product, or something that's analogous to an inner product between functions. So this idea is very familiar when we're talking about vectors, and we're going to use that idea to try to sort of generalize to the case of a function, or the inner product between two functions. So let's just go ahead and get started. So let's go ahead and just review this idea of a dot product between two vectors in space. So A dot B is just equal to A1 B1 plus A2 B2 dot dot dot, where A is some vector in some n-dimensional space and it has n components, and B is also some vector with n components. Now, we are taught in school, and in general, this notion isn't really very useful when you're considering a more generalized notion of an inner product, but we are taught that this is equivalent to A, just move this over, the magnitude of A times the magnitude of B, all times the cosine of theta, where theta is the angle between the vectors. Qualitatively, what this tells us is that if the angle between the vectors is greater than pi over 2, then the inner product is negative. If the angle is less than pi over 2, then the inner product is positive. And if the inner product is precisely pi over 2, then it's 0. So if the vectors are orthogonal, their inner product is 0, which is a way you can test for orthogonality. So let me just go ahead and just draw out these notions here just to make it a little bit more tangible. So I'll just call this A, and we can call this B. And this is the angle between them. It's some angle theta. So B and A are pointing roughly in the same direction, right? They're pointing both towards that first quadrant. So their inner product is greater than 0. It's positive. And the angle between them is less than pi over 2. So in this case here, theta is less than pi over 2 radians. Okay. Let's go ahead and check the case where A and B are orthogonal, where the angle between them is precisely 90 degrees or pi over 2 radians. So this is A, this is B, and the angle between them is pi over 2. Okay. Well, in this case here, their dot product would be 0, right? So A dot B is 0. And this is because when you think about it roughly, qualitatively, A and B are pointing in completely separate directions. B is going off this way and A is going off this way at 90 degrees. Okay, they don't share a projection. So if you try to project A onto B, you don't get anything. And if you try to project B onto A, you don't get anything either. In the first case that we considered, if you try to project B onto A, right, you do get something. This projection is precisely just this here. And if you try to project A onto the span of B, you also get something non-zero, right? You get some length. But in this case, you get precisely 0, because if you try to project B down onto A, you don't get anything. It's just 0. And now let's just go ahead and consider the final case of when the angle between A and B is greater than 0. So let's call this A, and let's just say that this is B. In this case, theta is actually greater than pi over 2. And as you can see, B is off in this direction, A is off in this direction, right? B is going down to that third quadrant, A is up into that first quadrant. And in this case here, if you try to actually project, right, B onto the span of A, well, let's just go ahead and just write out the span of A here. The span of A is simply the line that A lies on. Then you actually do get something that's non-zero. You get this little length here. okay, you get something that's non-zero. But it doesn't actually lie on the vector A because A and B point in opposite directions. So that is just a brief review of an inner product in the different cases, just so we can familiarize ourselves or refresh what exactly these values that you get mean. Okay, so now let's go ahead and think about what this means for a function. So let's just say we have some function here, some function of x, okay? So let's just say that this is f of x. Okay, and let's just go ahead and look at f on some particular interval. So let's just say that we're looking at it between some point A and then some point B. Now, let's say I wanted to, say you don't know what f of x is. Say I wanted to somehow describe f of x to you. Well, I can give you a collection of points, right? So, for example, I can give you 5 points only. Okay, let's just put a fifth one here. Didn't really space these out too well. But let's just say I give you these 5 points. Well, you're not going to be able to construct the function particularly well. Now, if I gave you more points, you'll be able to construct the function in an increasingly better fashion. So let's just say I give you a bunch of points that are equally spaced out. So we divide this interval up into a bunch of little segments, right? And I tell you the value of f of x at each of these points. Okay? From there, you can sort of get an idea of what f of x looks like. So what we can do is we can store these values for f of x as a vector, as a column vector. Let's just say that we can express f of x as a collection of values at a bunch of coordinates that are equally spaced out. Let's just say that we have n total points, okay, between this interval here. So here we're going to have n points, okay? Now, obviously, I can't give you an infinite number of points, right? I can only give you a finite number of points, a finite number of n points. Now, let's just let n go to infinity, however. Let's just say that I can give you an infinite number of points. Well, we have just expressed f as a vector in an infinite dimensional space. Okay? Now, let's think about how we would construct an inner product between f and some other function g. So let me just go ahead and draw another function here. Let's just say we can just call this here, just call this f of x. And let's just go ahead and call this right here g of x, right? And we're looking at it in between some interval. Let's just say that we're looking at it between this interval here, a, and another interval, b. Okay? How would we construct the inner product between these two functions? Well, if we were to do it naively in the fashion that we are familiar with, what we would say is we would simply just take, right, f, the first entry in that vector expression for f, times the first entry in the vector expression for g, right? However, we have an infinite number of points, and we're only looking at this function between an interval a and b, okay? We're only considering values of f and g that are in the interval between a and b. So naturally, when you want to take a sum and then extrapolate it to a case when you're dealing with the continuous function, you would use an integral. Therefore, we can go ahead and write f of x dot g of x in quotations, because this isn't precisely the old notion as the integral between a and b of f of g of x, rather, I just happened to write g first, all times f of x. So as you can see here, we're considering every value of g and every value of x and their products between the interval a and b, which is a natural way to generalize between the finite dimensional case and the case of a function, which is continuous. If you've learned something today, please consider subscribing, liking the video, and leaving something interesting in the comments. And I hope to see you next time.